Hi, welcome to Unexplained Mysteries of the Standard Model, Grand Unified Theories, and Limits on the Decay Rate of the Proton. In this video, we'll look at a real experimental result from particle physics, measuring, or more accurately, putting an upper limit on, the decay rate of the proton. We'll start by briefly going through some of the motivation to look for proton decay. Then we'll look at one way physicists at the Super-Kamiokande Experiment in Japan have experimentally looked for decaying protons, and we'll see their results. A link to the paper we'll be looking at from Super-Kamiokande is given in the video description below. Also, we'll be assuming some knowledge of the Boson distribution and Bayes' theorem in this video. You may be interested in checking out the Boson statistics playlist or the Bayesian playlist, available on this channel. Okay, let's get started. In particle physics, we have something called the Standard Model. It contains all of the known fundamental particles and says how they interact with each other. For example, the Standard Model contains quarks. Those called up and down quarks are contained in the proton and neutron found in the nuclei of atoms. The Standard Model also contains leptons, among them one you probably know, the electron. The Standard Model also contains particles which control the interactions, the electromagnetic strong and weak forces, between quarks and/or leptons. The most familiar of these is the photon, which mediates the electromagnetic interaction. You're probably very familiar with photons. In fact, you have two photon detectors, namely your eyes. Now, the Standard Model has had some amazing successes. You may have heard that the last particle predicted by the Standard Model, the Higgs boson, was discovered in 2012. For a more quantitative example, we can look at a quantity called the magnetic moment of the muon, and the muon is a type of lepton. To get the magnetic moment, we need something called the gyromagnetic ratio, G sub mu. The Standard Model tells us how to calculate G sub mu. It gives the theoretical value shown here, 2.00233183646. Meanwhile, the measured experimental value is something very similar. Here I should mention that the numbers in parentheses are the uncertainties in the last few digits, the last 2 digits or the last 3 digits respectively, of each of these quantities. Now, let's note that the two values, the theoretical value and the experimental value, differ by only 5 times 10 to the minus 9. Actually, in fact, although the two numbers agree impressively well, the small discrepancy between them is a current topic of investigation. Despite these successes, the Standard Model has some issues. For example, in the Standard Model, there are 3 families of quarks and leptons, and nobody knows why. Additionally, it doesn't predict the values of the masses of the quarks and leptons. In particular, in the Standard Model, particles called neutrinos are massless, but we experimentally know that they have non-zero, although very small, masses. The Standard Model also doesn't tell us anything about the nature of dark matter, whose existence is supported by many observations, but about which little else is known. And it doesn't successfully explain the baryon-antibaryon asymmetry of the universe, without which we wouldn't exist. For these reasons, among others, we try to come up with hypotheses about physics beyond the Standard Model. One class of hypotheses for physics beyond the Standard Model is grand unified theories, or GUTs. These models attempt to unify the interactions of the Standard Model into a single force. Grand unified theories also often predict that the proton will decay. Aside from grand unified theories, there are also other motivations to experimentally look for proton decay. But most generally, the Standard Model predicts that there would be no observable signal of proton decay. So, observation of proton decay would indicate the existence of some physics beyond the Standard Model, even if it's not a grand unified theory. Already, there are many proton decay modes with partial lifetimes experimentally constrained to be greater than 10 to the 30 years, and some of those are constrained to be greater than 10 to the 33 or 10 to the 34 years. Interesting values for the lifetime of the proton in grand unified theories tend to be between these limits and 10 to the 36 years. For some perspective, keep in mind that the current age of the universe is thought to be only about 14 times 10 to the 9 years. So you might wonder how we could have any hope of seeing a proton decay. It's true that if we watched a single proton and waited for it to decay, we'd probably be out of luck. But if we watch a lot of them for a long enough time, we might see some decay. This is what Super-Kamiokande does. They have watched for proton decay in 50 kilotons of water, which is of order 10 to the 34 protons, and they've been watching them for years. Now, particle decays are described by the Boson distribution. If we expect lambda decays on average over a certain period of time, the probability of actually having m decays in that time is given by the Boson distribution. So P Boson of m given lambda, which is equal to lambda to the m, e to the minus lambda, divided by m factorial. To get a feel for this equation, let's do a couple of quick numerical illustrations. So let's imagine that we watch 10 to the 34th protons for 1 year. And to make our first example simple, let's say that the probability of a given proton decaying in a given year is 1 part in 10 to the 34, or 10 to the minus 34. We would expect, on average, that 10 to the 34 times 10 to the minus 34, that's equal to 1, decay would happen during the year, so lambda equals 1. Let's see what our Boson distribution formula gives. Okay, so for lambda equal to 1, our Boson formula, that's lambda to the m, e to the minus lambda over m factorial, just becomes e to the minus 1 over m factorial. We thus get the following probabilities for various values of m. So the probability of m being 0, so that's seeing 0 events, is 36.8%. The probability of seeing 1 event is also 36.8%. The probability for seeing 2 events, that's m equals 2, is 18.4%, and so on. These values are illustrated in the plot at right. Now, let's see what would happen if the probability of a given proton decaying in 1 year was 1 part in 10 to the 33. So we still watch 10 to the 34 protons. This time, we would expect, on average, 10 to the 34 times 10 to the minus 33, which equals 10, decays during the year. So lambda equals 10. In the plot at right, we show the probability to obtain m decays during the year. We see that it peaks around m equals 10, but that values of m greater than 10 and less than 10 are both still allowed. Okay, conversely, what if the probability of a given proton decaying in a year was 1 part in 10 to the 35? Then lambda would be 10 to the 34 times 10 to the minus 35, which equals 0.1. So here we give a table of probabilities for different values of m. We can see that the probability to have m equals 0, that's to see 0 decays, is 90.5%. The probability to see 1 decay is 9%. The probability to see 2 decays is 0.5%, and the probability to see more than 2 decays is quite small. In this case, the probability to have 0 proton decays during the year dominates. Okay, so here we've given a quick idea of the relevance of the Poisson distribution for our present example of proton decay, and we've seen how the expected number of decays lambda affects the probability to actually observe m decays. Now, the Poisson distribution shows up in a lot of contexts. For more information, you can check out the Poisson Statistics playlist. You may also be interested in the playlist called Poisson Statistics Examples. Okay, let's get back to proton decay. So there are many ways a proton could potentially decay. Here, we'll just look at this first one. P goes to E plus pi naught. Here, the E plus is a particle known as the positron, and the pi naught is a neutral meson. Of the possible ways a proton could decay, P goes to E plus pi naught has the strongest experimental constraints. In fact, those are the experimental constraints from Super-Kamiokande that we'll discuss here. We should note that the list on the previous slide is only a small subset of decays physicists have experimentally tried to observe. So while the decay P goes to E plus pi naught is important, it is only part of the proton decay story. In the decay P goes to E plus pi naught, the pi naught itself decays down to 2 photons, which we label as gamma. So we end up with P goes to E plus pi naught, which goes to E plus gamma gamma. The mass of the 2 photon system should be compatible with that of a pi naught meson, and the mass of the 3 particle system should be compatible with that of a proton. Due to measurement errors, these measured masses will not match those of the pi naught and proton exactly. Okay, so Super-Kamiokande searches for P goes to E plus pi naught, which goes to E plus gamma gamma, in 50 kilotons of water. However, the E plus and the 2 photons each interact with the water, producing a shower of charged particles, which emit light in a cone known as Cherenkov radiation. So what Super-Kamiokande actually looks for is 3 rings of light in detectors near the outer edge of their water tank. And actually they look for 2 or 3 rings, as some decays might not successfully produce 3 distinguishable rings. So that's what the decay P goes to E plus pi naught would look like in Super-Kamiokande. When something like that occurs, we'll call it an event. Unfortunately, however, proton decay is not the only process that can look like that. These other processes, which we're not directly interested in, are called backgrounds, while the process we care about, p goes to e plus pi naught, is called our signal. So even if you see an event that looks like p goes to e plus pi naught, that doesn't necessarily mean you've discovered proton decay. You need to understand your backgrounds. Now, Super-Kamiokande reduces their backgrounds by selecting events which look like possible proton decays and rejecting those that don't. They do this by making selection cuts. For example, they keep only events where the total measured mass of the final products is close to the mass of the proton. While this reduces their experimental background, it doesn't eliminate it entirely. Additionally, they separate candidate events into two groups. Now, Super-Kamiokande watches for proton decays in water, which is made up of hydrogen and oxygen. If the proton did decay via p goes to e plus pi naught, the decays from protons in hydrogen atoms would typically fall into one of these groups, and decays from protons in oxygen would typically fall into the other. They estimate the background remaining after their selection cuts in these two groups to be 0.07 and 0.54 events, respectively. This means that if the proton does not decay via p goes to e plus pi naught, the number of events in each of these two groups would follow Poisson distributions with expected numbers of events lambda equal to 0.07 and 0.54, respectively. These would be background events mistaken for p goes to e plus pi naught during their entire multi-year dataset. These background estimates had uncertainties of approximately 30%, which Super-Kamiokande took as Gaussian distributed. Additionally, while the experimental selection is designed to choose signal p goes to e plus pi naught events and reject background events, some signal events, if they exist, end up getting rejected. The fraction of signal events, if they exist, that are chosen by the selection is called the efficiency. Super-Kamiokande's efficiencies were about 20% for each of the two groups of candidate events. Like the background numbers above, the efficiencies have uncertainties, which were around 10 to 20%. Now that's 10 to 20% of the efficiencies, which were themselves about 20%. So these effects mean that the number of candidate events you select in your data is not exactly equal to the number of protons which decay in your experiment. There can be extra events from background processes which aren't proton decay, but which you mistake for proton decay events. And if there are some protons that decay in your experiment, you might not catch them all. Also, the rate of background processes and the efficiency to see your signal events have uncertainties. So all of these effects need to be taken into account. So Super-Kamiokande analyzed their data and found no events that passed their selection for p goes to e plus pi naught. They then used this fact to place a limit on the rate at which a proton would decay via p goes to e plus pi naught. The full details of how they arrived at this limit are a bit complicated. So here, let's go through a toy calculation, which gives the basic idea of how they got their limit, but which avoids a lot of complications. To do this toy calculation, let's imagine we watched 10 to the 34 protons for 1 year. So this is somewhat smaller than Super-Kamiokande's dataset. We'll take our efficiency for spotting protons decaying via p goes to e plus pi naught as 100% with no error bar, instead of Super-Kamiokande's efficiencies and their error bars. Now let's call the probability for a given proton to decay in a year R. After 1 year, we'll see 10 to the 34 times R proton decays on average. We'll also take the expected background in that year as 0.6 events, again with no uncertainty. Super-Kamiokande's were 0.07 and 0.54 events for the two groups of events with their respective uncertainties. Given these simplifications, the number of events we should see in 1 year, on average, is 10 to the 34 times R plus 0.6. So that's 10 to the 34 R signal events and 0.6 background events. The actual number of events M that we see is probabilistic, given by a Poisson distribution for lambda equal to 10 to the 34 R plus 0.6. So our Poisson formula that we saw earlier becomes the Poisson probability to observe M events when lambda are expected, which equals lambda to the m e to the minus lambda over m factorial, goes to 10 to the 34 R plus 0.6, all raised to the m power, e to the minus 10 to the 34 R plus 0.6, all divided by m factorial. Now, Super-Kamiokande observed 0 p goes to e plus pi naught events, and we will assume we do the same for our toy calculation, so m equals 0. Now, the Poisson probability, p Poisson of m given lambda, is particularly simple for the case m equals 0. So the Poisson probability for m equals 0 for some value of lambda equals e to the minus lambda, which in this case is e to the minus 10 to the 34 R plus 0.6. Okay, so we have that our Poisson probability to observe 0 events is equal to e to the minus 10 to the 34 times R plus 0.6. This tells us the probability to observe m equals 0 events given a certain value of R. But that's not what we want. We have observed m equals 0 events, and now we want to know if we can rule out certain ranges of R. To do this, we'll use something called Bayes' theorem. Our goal is to make a statement like this. Given that our experiment observed m equals 0 events, there is a 90% chance that the probability R for a given proton to decay in a year is less than some number. What we have to do is figure out what number goes in the some number part of that statement. Bayes' theorem will help us do that. To just make the notation a bit cleaner, let's define the expected number of signal events, S, to be 10 to the 34 R. So lambda is equal to S plus 0.6, where again 0.6 is the number of background events. We write the probability of observing m equals 0 events as the Poisson probability to observe 0 given lambda, where now lambda is equal to S plus 0.6. So this is equal to e to the minus s plus 0.6. We'll switch back to the r notation at the end. Now, with this new notation, our statement is, given that our experiment observed m equals 0 events, there is a 90% chance that the average number of proton decays, s, in our experiment in a year is less than some number. So we want to determine the some number part of that statement. Let's call that number S90. So our statement can be written as the probability that S is less than S90, given that m equals 0, is equal to 90%. And now our goal is to determine S90. So Bayes' theorem requires that we make some assumptions about the probability for S to fall in certain ranges, evaluated without knowing the result of our experiment. So let's make some assumptions. The number of expected decays cannot be negative, so S must be greater than or equal to 0. Let's take S to be somewhere between 0 and 10. We could make the upper edge of the range 10 or 100 or infinity, and it wouldn't change the result very much. Let's also assume that all values of S between 0 and 10 are equally probable. To make things concrete, let's divide the range of S between 0 and 10 into 1,000 equally spaced intervals, or bins. And we should note that we're dividing the range into bins to illustrate the method without using calculus. If you've had calculus, you may realize that this calculation could be done much more simply. Okay, so before the measurement, the probability for S to fall into any of these intervals is 1 part in 1,000, or 0.001. Now, let's use Bayes' theorem to see what happens after the measurement. Bayes' theorem looks like this, and it's read as follows. The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. For more information on Bayes' theorem, such as what it means, how it's derived, and some examples, you can check out the Bayesian playlist on this channel. Let's start by getting the probability, given that m equals 0, that S falls into the ith interval. There are 1,000 intervals between 0 and 10, so each one has a length of 0.01, or 1 over 100. If S falls into the ith interval, S is between I minus 1 over 100 and I over 100. Before the experiment, the probability that S falls into the ith interval is 0.001, because there are 1,000 intervals. Let's apply Bayes' theorem to get the probability that S falls into the ith interval, given that we observed no events, that m equals 0. Okay, so again, Bayes' theorem says the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. For our situation, we set A equal to S falls into the ith bin, or in other words, S is between I minus 1 over 100 and I over 100. And we set B equal to m equals 0. So we get that the probability that S falls into the ith bin, that's that S is between I minus 1 over 100 and I over 100, given that m equals 0, is equal to the probability that m equals 0, given that S falls into the ith bin, times the probability that S falls into the ith bin, all divided by the probability that m equals 0. So, we had the probability, given that m equals 0, that S would fall into the ith bin, or equivalently that S would be between I minus 1 over 100 and I over 100. So the probability that S would fall into the ith bin, given that m is equal to 0, is equal to the probability that m equals 0, given that S falls into the ith bin, times the probability that S falls into the ith bin, divided by the probability that m would equal 0. So let's evaluate this. Let's start with evaluating the probability that S falls into the ith bin. Now, the probability that S falls into the ith bin is the probability that S falls into the ith bin evaluated without information about m. This is the probability that we assigned at the beginning. There were 1,000 bins, and S was equally likely to fall in any of them. So the probability that S falls in the ith bin is just 0.001, 1 over 1,000. Okay, so now our previous expression becomes the same thing, except that now we've substituted in for the probability that S falls into the ith bin, that's the second term in the numerator on the right, is now 0.001. Okay, so now we have that new version of our expression. Let's look at the probability that m equals 0, given that S falls in the ith bin. So this is the first factor in the numerator on the right-hand side. We saw that the Poisson probability to obtain m equals 0, given S and 0.6 background events, the Poisson probability to get 0 given S plus 0.6, was equal to e to the minus S plus 0.6. Now here, S is between I minus 1 over 100 and I over 100, but these are very close to each other. Let's just approximate S as equal to I over 100. Okay, so using S is approximately equal to I over 100, and that the Poisson probability to observe 0 events when S plus 0.6 are expected is equal to e to the minus S plus 0.6, we get that the probability for m to equal 0, given that S is in the ith bin, is approximately equal to the Poisson probability to observe 0 events when I over 100 plus 0.6 are expected, and that equals e to the minus I over 100 plus 0.6. Okay, so now our previous expression becomes the same thing, except that now on the right-hand side in the numerator, we have substituted in e to the minus I over 100 plus 0.6 for the probability that m would equal 0 given that S is in the ith bin. Okay, so now we have the new version of our equation. To evaluate this, we still need to get the probability that m equals 0, so the denominator on the right-hand side. To get the probability that m equals 0, let's remind ourselves of what the numerator is on the right-hand side. Okay, so e to the minus I over 100 plus 0.6 is the probability of having m equals 0 given that s is in the ith bin. 0.001 is the probability of s being in the ith bin. So their product, e to the minus I over 100 plus 0.6 times 0.001 is the probability of having m equals 0 and s in the ith bin. If we were to sum this over all bins, we would have the probability of having m equals 0 and s in any bin. But as s must be in some bin, that's just the probability of having m equals 0. So that's just the probability of m equals 0, which is what we want. Thus, summing over all 1,000 bins, we get that the probability for m to equal 0 is equal to the sum over j from 1 to 100 e to the minus j over 100 plus 0.6 times 0.001. And here we have renamed the index j. Now we can put this back into our expression. So now we have the probability for s to be in the ith bin, given that m equals 0, is equal to e to the minus I over 100 plus 0.6 times 0.001, all divided by the sum over j from 1 to 1,000, e to the minus j over 100 plus 0.6 times 0.001. Okay, so we've almost got this. Note that the factors of 0.001 and e to the minus 0.6 cancel between the top and bottom. So the probability for s to be in the ith bin, given that m is equal to 0, is equal to e to the minus I over 100 divided by the sum over j from 1 to 1,000 e to the minus j over 100. This is the probability, given m equals 0, that s is in the ith bin. Now let's use this to get the result we really want. Okay, so we want to make a statement like, given that our experiment observed m equals 0 events, there is a 90% chance that the average number of proton decays s in our experiment in a year is less than s90. Mathematically, we say that the probability that s is less than s90, given that m equals 0, is equal to 90%. And now we need to determine s90. To do this, we start adding up the probabilities, given m equals 0, for s to be in the ith bin, over the bins starting from the first bin, so in other words at s equals 0. We add up these bins until we get to 90%. When we get to 90%, we stop. The value of s at that bin, or equivalently I over 100 at that bin, is s90. So mathematically, 90% is equal to the sum over I from 1 to 100 times s90, e to the minus I over 100, divided by the sum over all bins j, e to the minus j over 100. If we do this procedure, we find that s90 is equal to 2.3. So we conclude that in our toy example, given m equals 0, the probability that s is below 2.3 is 90%. We can convert this back to a rate using s equals 10 to the 34r. So we can also say that given m equals 0, the probability that r is less than 2.3 times 10 to the minus 34 is 90%. The mean lifetime tau is 1 over r, so the probability, given m equals 0, that tau is greater than 4.3 times 10 to the 33 years is 90%. That is the result for our toy calculation. Our toy calculation roughly outlines how Super-Kamiokande arrived at their limit. However, they carefully included their efficiencies and uncertainties, so their calculation is more involved, but along the same lines. From their 0 events, they derived a lower bound on the mean partial lifetime for p goes to e plus pi naught. So that's the mean lifetime of the proton if that was its only possible decay, of 1.6 times 10 to the 34 years. As above, this lower bound is defined to mean that the probability that the mean partial lifetime is greater than 1.6 times 10 to the 34 years is 90%. We'll make one minor point about the Super-K result. As shown above, they used Bayes' theorem in deriving their limit on the mean partial lifetime of p goes to e plus pi naught. Bayes' theorem required some initial assumptions about the probability distribution of the decay rate. Some experiments choose to not make these assumptions and thus define their limits differently. This is just something to be aware of when reading the experimental literature. Okay, let's briefly summarize. Here we've taken a look at a real result from modern particle physics, proton decay. We saw why proton decay is interesting and one way physicists are searching for it experimentally. Also, this has been a real example of how tools such as the Boson distribution, the Gaussian distribution, and Bayes' theorem arise in producing scientific results. Feel free to leave questions in the comments.